Venus looks beautiful from far away, a bright white jewel near the sun, glowing softly in the evening sky, almost peaceful enough to be mistaken for Earth's twin. But beneath those clouds, Venus is not peaceful. It is a planet that was destroyed slowly, not by an asteroid, not by war, not by one sudden disaster, but by heat, pressure, chemistry, and a runaway greenhouse effect so powerful that the entire planet became a warning. Its oceans, if they once existed, vanished. Its sky turned toxic. Its surface became hot enough to melt lead, and its atmosphere grew so heavy that standing there would feel like being crushed beneath an ocean. Tonight, we are not just asking what Venus is. We are asking what killed it. Was it always doomed because it formed too close to the sun? Or did Venus once have a real chance to become a living world like Earth? Before we begin, if you enjoy calm, cinematic space documentaries made for sleep, mystery, and deep cosmic questions, make sure to subscribe to Theories Before Sleep. Now get comfortable, because the death of Venus may be the most terrifying warning in the solar system. Venus today is the most hostile world in the inner solar system. Not Mars, not Mercury, not the Moon. Venus. From far away, it looks almost gentle, a bright white planet wrapped in clouds, shining like a jewel near the sun. It is often called Earth's sister because it is nearly the same size, nearly the same mass, and formed in the same region of the early solar system. But the resemblance ends at the clouds. Beneath them, Venus is a nightmare of heat, pressure, poison, and silence. The surface temperature is around 465 degrees Celsius, hotter than Mercury, even though Mercury is closer to the sun, hot enough to melt lead, hot enough to destroy ordinary machines, hot enough that any unprotected human presence would be impossible almost instantly. And the heat is only the beginning. The atmospheric pressure on the surface is about 92 times greater than Earth's. Standing on Venus would feel like being nearly a kilometer beneath Earth's ocean, except instead of cold, dark water above you, there is a crushing sky of carbon dioxide. The air is not air in any human sense. It is mostly carbon dioxide, thick and heavy, with clouds of sulfuric acid high above. The clouds do not bring soft rain like Earth's clouds. They form droplets of acid that fall through the atmosphere, but the lower air is so hot that they evaporate before they ever reach the ground. So Venus has clouds. It has something like rain, but it has no mercy. The sky is yellowish and choking. The ground is volcanic and dry. The atmosphere is so dense that the surface is dim, even in daylight. Sunlight struggles through the endless cloud cover, reaching the ground as a dull orange glow. There are no oceans, no rivers, no forests, no blue sky, no breathable air, no place where a human body could survive naturally for even a moment. A spacecraft landing there does not land in a normal environment. It descends into a furnace under pressure. The Soviet Venera landers proved this better than anything else. They reached the surface, sent back images, measured the conditions, and then died under the punishment of Venus. Their survival was measured in minutes, not years, not months, minutes. That is Venus today, a planet that looks beautiful from Earth but becomes terrifying the closer we get. And yet, Venus was not always like this. That is the part that changes everything. Because Venus is not just a hell world. It may be a world that lost something, a world that once had a chance. A world that may have been warm, wet, and perhaps even habitable before the catastrophe began. For a long time, people imagined Venus as a tropical planet hidden beneath clouds. Before spacecraft showed us the truth, some thought there might be jungles below the white atmosphere, oceans beneath the haze, maybe a humid world under permanent cloud cover. The reality turned out to be the opposite. But modern science has brought back a different version of that old dream, not as fantasy, but as possibility. Venus may once have had oceans, not oceans like a small temporary pond. Real water, liquid water, enough to change the climate, shape the surface, and perhaps keep the planet habitable for an enormous stretch of time. Computer models suggest that ancient Venus could have maintained liquid water for billions of years under the right conditions. Some simulations show a world with clouds, rainfall, oceans, and a climate stable enough to last for 2 or even 3 billion years. Think about what that means. 2 or 3 billion years. That is longer than complex animals have existed on Earth. Longer than forests. Longer than dinosaurs. Longer than flowers. Longer than human beings by an almost absurd amount. If those models are correct, Venus may not have been briefly habitable. It may have been habitable for a truly planetary age, a world where water stayed long enough for chemistry to deepen, long enough for climates to cycle, long enough for oceans to interact with rock, long enough, perhaps, for life to have had a chance. We do not know if life ever appeared there. There is no proof. But the possibility alone is haunting, because it means the Venus we see today may be the corpse of a once living possibility, a planet that might have had oceans under sunlight, a planet that might have had shorelines, a planet where rain may once have fallen from normal clouds into liquid seas, a planet that, from space, might once have looked blue and white, almost like Earth. This is why Venus is so important. It is not only a warning about heat, it is a question about fate. How does a planet so similar to Earth become so different? Venus and Earth were born from the same ancient disk of gas and dust around the young sun. They formed from similar material. They grew in the inner solar system. They became rocky worlds with gravity strong enough to hold atmospheres. Their sizes are close. Their masses are close. Their densities are close. They are sisters in almost every basic physical way. But one became home. The other became hell. Earth became a world of oceans, clouds, continents, oxygen, life, and changing seasons. Venus became a world of pressure, acid clouds, runaway heat, and dry volcanic plains. That split is one of the deepest mysteries in planetary science because it asks a terrifying question. Was Venus doomed from the beginning? Or did something go wrong later? If Venus once had oceans, then its death was not immediate. It was not born as the hell we see today. It may have passed through a long, calm chapter first, a chapter now almost completely erased. And that is the difficulty. Venus does not easily give up its past. Its surface is hidden beneath thick clouds. We cannot simply look down with ordinary cameras from space and see everything clearly. Radar must be used to map the ground. The atmosphere blocks visible views, and the surface conditions destroy landers quickly. Even worse, Venus appears to have resurfaced itself. Much of the visible surface is geologically young compared with the age of the planet. Lava flows, volcanic plains, and tectonic deformation may have covered or altered older terrain. The record of ancient oceans, if it exists, is damaged, buried, or transformed. Earth preserves its history through rocks, sediments, fossils, ocean chemistry, and continental crust. Venus keeps its memory locked behind heat and cloud. But not everything is erased. Some parts of Venus may still hold clues. One of the most important is the tessera terrain. Tesserae are strange highland regions on Venus, heavily deformed, folded, ridged, fractured, and complex. They look different from the surrounding volcanic plains. They are among the oldest looking surfaces on the planet, and because of that, scientists study them as possible windows into Venus's early history. The tesserae may contain rocks that formed under conditions very different from modern Venus. Some researchers have wondered whether these highlands could be ancient continental-like regions. Not continents exactly like Earth's, but crustal areas that may have formed when water was still present and the planet's surface chemistry was different. If Venus had oceans, its highlands may once have risen above them, like continents or islands. Imagine that. The places we now see as tortured highlands under a toxic sky may once have been ancient landmasses surrounded by water. A dark, volcanic world today, but perhaps once a planet with coastlines. The word continent changes the feeling of Venus, because continents imply more than rock. They imply contrast, land and sea, highlands and basins, weathering, rivers, minerals shaped by water. The possibility that Venus once had continental-like crust suggests a planet with a more complex and Earth-like past than its modern surface admits. Then there are the valleys and channels. Venus has long channels carved into its surface, some stretching for thousands of kilometers. Many are believed to be volcanic in origin, formed by lava flows rather than water. Modern Venus is too hot and too dry for rivers as we know them. But when we talk about ancient Venus, the interpretation becomes more open and more haunting. Some surface features raise questions about what processes shaped them long ago. Could any of them preserve hints of ancient liquid movement? Could some topography have been influenced by water before the planet became completely dry? Could older landscapes have been buried beneath volcanic plains? We do not yet know enough, and that uncertainty is what makes Venus so fascinating. Mars gives us ancient riverbeds openly, carved into dry ground under a thin sky. Venus hides its evidence under clouds, heat, pressure, and geological violence. Mars looks dead, but readable. Venus looks dead and secretive. To understand what killed Venus, we have to reconstruct a lost planet from fragments, from atmosphere, from chemistry, from radar maps, from computer models, from strange highlands, from volcanic plains, from the absence of water, and from the fact that two sister worlds ended so differently. Now imagine Venus 3 billion years ago. Not the Venus we know, not the orange furnace, not the acid clouds, not the crushing atmosphere. Imagine a younger Venus rotating slowly beneath a bright sun. The sunlight is stronger than Earth's, but the planet may be wrapped in thick reflective clouds. Those clouds could bounce much of the sunlight back into space, helping the planet stay cooler than we might expect. Below the clouds, oceans spread across lowlands. Maybe not deep global oceans like Earth's. Maybe shallow seas, maybe broad tropical waters, maybe islands and highlands rising above the surface. The sky might be bright, cloudy, humid, perhaps white and blue from space. If you were far away, looking at the inner solar system, ancient Venus might not have looked like a doomed world. It might have looked alive with possibility, a blue and white planet close to Earth's size, a twin, a second ocean world, from a distance, perhaps almost indistinguishable from Earth. Two bright planets orbiting the young sun, both with clouds, both with water, both with rocky surfaces, both carrying the ingredients that make habitability possible. One closer to the sun, one farther out, one slowly moving toward disaster, one holding its balance long enough for life to transform it. This image is beautiful, but also painful, because we already know how the story ends. Whatever oceans Venus may have had are gone. Whatever rivers may have flowed are gone. Whatever coastlines may have existed are gone. Whatever climate once held the planet in balance collapsed. Something pushed Venus past a threshold, and once it crossed that line, there may have been no way back. That is the real terror of Venus. Not that it is hot, not that it is dangerous, but that it may have been habitable first. A dead world is sad. A world that killed its own habitability is frightening, because it means planets can change completely. A world can begin with oceans and end as an oven. A sky can begin with clouds and end as poison. A surface that once touched water can become dry enough to preserve almost no trace of it. Habitability is not permanent, it is a balance. And balances can break. This is why Venus matters to Earth. Because Earth is not protected by magic. Earth survives because many systems remain in balance. Atmosphere, oceans, clouds, carbon cycle, plate tectonics, magnetic field, life and distance from the sun. We often think of Earth as stable because it has been our home for all of human history. But human history is tiny. Planets operate on millions and billions of years. Venus reminds us that a rocky planet can change beyond recognition. And if Venus once had oceans for billions of years, then the question becomes sharper. What exactly killed it? Was it simply too close to the sun? Did sunlight slowly increase until the oceans began to evaporate? Did water vapor build up in the atmosphere and trap more heat? Did volcanoes pour carbon dioxide into the sky faster than the planet could remove it? Did Venus lack the plate tectonics needed to bury carbon into rock? Did its slow rotation change cloud patterns and climate? Did the sun strip away its water after ultraviolet light broke water vapor apart? Was there one catastrophe, or was it a chain reaction? A planet does not always die from a single blow. Sometimes it dies from feedback. A little more heat evaporates more water. More water vapor traps more heat. More heat evaporates more water. The oceans shrink. The atmosphere thickens. Carbon dioxide accumulates. The surface warms further. Rocks change. Volcanoes continue. The sky becomes a trap, and slowly, the planet passes the point where oceans can survive. That is where the story of Venus becomes the story of a murder with many suspects. The sun, carbon dioxide, water vapor, volcanoes, chemistry, slow rotation, missing plate tectonics, time. Each one may have played a role, but the victim was habitability itself. The Venus we see today is the result, not the beginning. Its surface temperature, its crushing pressure, its acid clouds, its dry plains, its strange highlands, and its lost water are the evidence left behind after the death. And somewhere under that evidence, hidden in radar shadows and ancient terrain, is the memory of a different world. A Venus with oceans, a Venus with clouds that cooled it, a Venus that may have stayed habitable longer than we once imagined, a Venus that had a chance. That is what makes it so tragic. Venus was not some distant exoplanet in another star system. It was next door. It formed beside us. It shared the same young sun. It had nearly the same size as Earth. It may have carried water across deep time, and then it crossed a line. Earth did not. At least, not yet. That difference is the most important question in planetary science. Why did Earth remain alive while Venus died? What saved one sister and destroyed the other? And when we look at Venus, are we looking only at a failed planet or at a warning? A future Earth must never approach. Tonight, the story begins before the death, before the runaway heat, before the oceans vanished, before the atmosphere became a prison, before Venus became the brightest warning in our sky. It begins with the possibility that this world was once blue, that beneath the planet we now fear, there was once a planet we might have recognized, a sister, a mirror, a second Earth that lost the fight for balance. And if we want to know what killed Venus, we first have to understand what Venus may have been before it died. The real killer of Venus was not one sudden disaster. It was not a single impact, not one volcanic eruption, not one bad day in the history of the planet. It was a process, a slow, quiet, invisible process that began with warmth and ended with a world turned into an oven. The runaway greenhouse effect. To understand what happened, we first have to understand what a greenhouse effect really is. Because the greenhouse effect is not evil by itself. On Earth, it is one of the reasons we are alive. Our planet receives sunlight. Some of that sunlight reflects back into space from clouds, ice, oceans, and bright surfaces. But much of it reaches the ground and warms the surface. Then Earth releases that heat back upward as infrared radiation. If there were no greenhouse gases in the atmosphere, much of that heat would escape directly into space. Earth would be far colder. The oceans could freeze. Life as we know it would struggle to exist. But gases like water vapor, carbon dioxide, methane, and others absorb some of that outgoing heat and send part of it back downward. They act like a thermal blanket around the planet. Not a solid blanket, not a glass dome, but a layer of gases that slows the escape of heat. This is why Earth is warm enough for oceans, rain, forests, animals, and human life. The greenhouse effect is not the enemy. The problem begins when the balance breaks. A little greenhouse effect creates habitability. Too much greenhouse effect creates a trap. And Venus crossed that line. In the beginning, ancient Venus may have had water on its surface. Oceans, seas, perhaps shallow basins beneath thick reflective clouds. The planet received more sunlight than Earth because it orbited closer to the sun. But under the right conditions, clouds may have reflected enough energy away to keep the surface stable for a long time. For millions of years, maybe billions, Venus may have remained balanced, warm but not destroyed, cloudy but not dead, wet but not doomed yet. But the sun was changing. Stars do not remain perfectly constant across deep time. Our sun has gradually brightened since its youth. Very slowly, across billions of years, the amount of energy reaching the planets increased. On Earth, this gradual brightening was moderated by long-term climate systems. Weathering, oceans, carbon cycling, geological processes, and life all helped shape the balance. Earth did not stay exactly the same, but it stayed within the range where liquid water could survive. Venus was closer. That difference mattered. A small difference in distance from the Sun can become enormous over planetary time. Venus received more solar energy from the beginning, and as the Sun brightened, that extra energy became more dangerous. At first, the change may have been subtle, a slightly warmer ocean, more evaporation, more humidity in the air, thicker clouds, a warmer lower atmosphere, nothing that looked like the end. If you could stand on ancient Venus during that stage, you might not know the planet was moving toward catastrophe. The oceans would still be there. Clouds might still drift across the sky. Rain might still fall. The planet might still look alive with possibility. But climate systems can hide danger until a threshold is crossed. The key was water vapor. Water vapor is not just moisture. It is a powerful greenhouse gas. When water evaporates from an ocean, it enters the atmosphere. Once there, it traps heat. That extra trapped heat warms the surface further. A warmer surface causes more ocean water to evaporate. More evaporation creates more water vapor. More water vapor traps more heat. This is the loop. Warmth creates vapor. Vapor creates warmth. Warmth creates more vapor. And once that loop becomes strong enough, the planet no longer simply warms. It runs away. This is the runaway greenhouse effect. It is not just warming. It is warming that feeds itself. A feedback loop that takes control. On Earth, water vapor also amplifies warming, but Earth still has mechanisms that help regulate climate. Water condenses into clouds and rain. Oceans absorb heat. Carbon dioxide can be removed from the atmosphere over long timescales through rock weathering and buried in sediments. The planet has ways of moving heat, storing carbon, and returning water to the surface. Venus lost the balance. As ancient Venus warmed, its oceans evaporated faster. The atmosphere became wetter. The greenhouse effect grew stronger. The surface became hotter. The oceans warmed further. The air held even more water vapor. And slowly, the planet approached a point where cooling itself became impossible. This is the terrifying thing about tipping points. Before the tipping point, a system can recover. After the tipping point, the system begins driving itself forward. Venus reached a stage where the sunlight it absorbed, combined with the greenhouse heat trapped by its thickening atmosphere, pushed the climate beyond stability. The oceans could no longer remain oceans. They became part of the air. Imagine the process not as one explosion, but as a planetary fever rising across ages. The seas grow warmer, coasts retreat, rain patterns change, cloud systems thicken, the lower atmosphere becomes heavy with moisture. The surface heat rises beyond anything familiar. Eventually, the oceans begin to boil away. Not all at once like a pot on a stove, but in the sense that liquid water can no longer remain stable over geologic time. More and more of it enters the atmosphere, and less returns permanently to the surface. The sky becomes the ocean. Venus's water, once spread across the ground, becomes suspended above it. A planet that may have once reflected blue and white from space begins to change into something stranger, brighter, and more dangerous. The atmosphere grows denser with greenhouse gases. The heat becomes more trapped. The surface becomes less like a shoreline world and more like a drying furnace. Then comes the second part of the catastrophe. The water does not simply stay in the atmosphere forever. High above the surface, in the upper atmosphere, ultraviolet light from the sun begins breaking water molecules apart. Water is made of hydrogen and oxygen. When ultraviolet radiation splits those molecules, the light hydrogen atoms can escape into space. Hydrogen is extremely light. Once it reaches the upper atmosphere, it can be lost forever, especially on a planet without the right protection and with the sun constantly pouring energy into the upper air. So Venus did not simply move its oceans into the sky. It began losing them to space. Hydrogen escaped, atom by atom, year by year, age by age. The water was not just evaporated, it was destroyed as water. The oxygen left behind did not build a breathable atmosphere like Earth's. Venus had no biosphere like Earth's to maintain free oxygen. Instead, oxygen likely reacted with surface rocks and minerals, becoming locked into the crust through chemical reactions. Hydrogen left forever. Oxygen was trapped. The water disappeared permanently. That is one of the most tragic parts of Venus's story. A planet might recover from temporary warming if its water remains. It might cool again, rain might return, oceans might stabilize. But once hydrogen escapes into space, the ocean is not waiting somewhere else. It is gone, not frozen underground, not hidden under ice, gone from the planet. Venus lost the ingredient that could have made recovery possible. The death sentence was not simply heat, it was water loss. Without oceans, Venus lost one of the great stabilizing forces a rocky planet can have. Oceans absorb heat. They help regulate climate. They interact with carbon dioxide. They allow weathering. They create clouds and rainfall. They shape the chemistry of a world. When Venus lost its oceans, it lost its climate memory. The surface was exposed. Dry rock replaced coastlines. Heat replaced rainfall. The air, already thickening, became more and more dominated by carbon dioxide. And without liquid water on the surface, carbon dioxide could no longer be removed effectively through the kinds of water rock cycles that help Earth remain habitable. On Earth, carbon dioxide dissolves in rainwater and seawater. It reacts with rocks. Over long timescales, some of that carbon becomes locked away in minerals and sediments. Plate tectonics and volcanoes then recycle carbon between the interior and atmosphere. It is not a perfect thermostat, but it is a thermostat. Venus lost the water part of that system, so carbon dioxide stayed in the sky. Volcanoes could keep adding more. The atmosphere became heavier. The greenhouse effect became stronger. The surface became hotter. And the planet moved further and further from anything that could support oceans again. This is why the runaway greenhouse is so frightening. It does not kill a planet in one step. It removes the recovery tools. First, extra heat increases water vapor. Then water vapor traps more heat. Then oceans evaporate. Then ultraviolet light breaks water apart. Then hydrogen escapes. Then oxygen reacts away. Then the planet becomes dry. Then carbon dioxide remains. Then the atmosphere thickens. Then the surface becomes permanently scorched. Each step makes the next easier. Each loss makes recovery harder. By the time Venus became the world we see today, the original balance was not just damaged, it was erased. The atmosphere became a crushing blanket of carbon dioxide. The surface temperature rose far above the boiling point of water. The pressure built until the lower atmosphere became dense and heavy. Clouds of sulfuric acid filled the sky. The entire planet settled into a stable hell. Stable is the important word. Venus today is not unstable in a way that is trying to return to habitability. It has found a new balance, a terrible balance, a world where the heat is trapped so effectively that day and night are both brutally hot. A world where the surface does not cool the way Mercury's night side cools. A world where the thick atmosphere moves heat around the planet until almost everywhere is baked. That is why Venus is hotter than Mercury. Mercury is closer to the Sun, but it has almost no atmosphere. It burns in sunlight and freezes in darkness. Venus has a massive atmosphere. It traps heat everywhere. Even the night side cannot escape. Even the poles remain furnace-like. The greenhouse effect has wrapped the entire world in heat. There is no safe shadow, no cold night, no polar refuge. The atmosphere itself is the prison. And this prison was built from feedback. That is the true killer. Not the sun alone, not carbon dioxide alone, not water vapor alone, not volcanoes alone, but a chain reaction between sunlight, oceans, atmosphere, and chemistry. Venus crossed a critical threshold, and after that, the planet became its own executioner. Its oceans became vapor. Its vapor made it hotter. Its heat destroyed the oceans further. Its lost water removed the possibility of cooling. Its dry surface left carbon dioxide in control, and its atmosphere became a machine that could only hold heat. This may be the most dramatic planetary transformation in our solar system's history. Mars lost much of its atmosphere and became cold. Mercury remained airless and extreme. Earth stayed balanced, but Venus may have gone from ocean world to furnace world, from possible habitability to total hostility, from sister planet to warning planet. And what makes it even more unsettling is that the process did not need to begin with something spectacular. It may have begun with a little more sunlight, a little more evaporation, a little more water vapor, a little more heat. Planetary disasters are not always loud at first. Sometimes they begin quietly, as a small imbalance repeated for long enough. A tiny push in one direction, then another, then feedback, then acceleration, then no return. This is why Venus matters when we think about Earth. Earth is not Venus. Earth is farther from the Sun. Earth has oceans, plate tectonics, life, a different atmosphere, and a different climate history. The modern human-driven climate problem is not the same as Venus's total runaway greenhouse. Earth is not about to become Venus tomorrow. But Venus shows us something deeper. It shows that habitability depends on limits. A planet can tolerate change only within a certain range. Push too far, and the systems that once stabilized climate can become systems that amplify disaster. Water, the ingredient of life, became part of Venus's destruction once it filled the atmosphere as vapor. Clouds, which can cool a planet by reflecting sunlight, could not save it forever once the energy balance shifted too far. A thick atmosphere, which can protect a world, became a crushing heat trap. The same ingredients that support life under one balance can destroy habitability under another. That is the real truth. Venus was not killed by something alien. It was killed by physics, by sunlight, by heat, by vapor, by chemistry, by feedback, by the slow failure of balance. And once the oceans were gone, the planet could not simply choose to return. The water had escaped into space. The carbon dioxide remained. The surface was dry. The greenhouse trap was complete. This is the point where Venus stopped being a lost ocean world and became the planet we know now. A world where heat cannot leave easily. A world where pressure crushes the ground. A world where clouds hide the surface, not with water, but acid. A world that shines beautifully in our sky because its cloud tops reflect sunlight, while below them the surface is dead, dry, and burning. The brightest planet became the darkest warning. And it all began with a climate system that crossed its limit. When we ask what killed Venus, The answer is not simply the greenhouse effect. A normal greenhouse effect keeps planets alive. The answer is the runaway greenhouse effect. The moment warming stopped being a condition and became a chain reaction. The moment oceans stopped cooling the planet and started feeding the heat. The moment water stopped being a future and became vapor on its way to space. That was the death of Venus. Not a sudden murder, a planetary transformation. A slow crossing of a line that could not be uncrossed. And after that line, the sister of Earth disappeared forever beneath the clouds. The runaway greenhouse effect was not the end of Venus's destruction. It was the beginning of a deeper collapse. Because while the atmosphere was trapping more heat, while the oceans were disappearing into vapor, while hydrogen was escaping into space and the sky was becoming heavier, something else was happening beneath the surface. Venus was not dying only from above. It was changing from below. Inside the planet, heat was building, rock was melting, pressure was shifting. The interior of Venus was preparing to rewrite the entire surface. And when Venus's geology finally turned violent, it may have erased almost everything that came before. Today, Venus is one of the most volcanic worlds we know. Its surface is covered with volcanoes. Not a few, not dozens, thousands. More than 1,600 major volcanic structures have been identified. And if smaller volcanic features are counted, the number becomes far greater. Domes, shields, lava plains, volcanic rises, coronae, rift zones, collapsed calderas, and enormous flow fields cover the planet. Venus is not just a planet with volcanoes. Venus is a planet shaped by volcanoes. From orbit, radar maps reveal a world where lava has been one of the dominant forces in its history. Since ordinary cameras cannot see through the thick clouds, spacecraft used radar to map the hidden ground below. What they found was not an Earth-like planet with familiar continents and ocean basins. They found a volcanic world, a surface built, buried, and scarred by molten rock. This is where Venus becomes even more mysterious. The surface appears surprisingly young. Not young compared to human history. Young compared to the age of the planet. Venus is about the same age as Earth, around 4.5 billion years old. But much of the surface we see today may be only 300 to 500 million years old. That sounds ancient to us. But for a planet, it is recent. It means the visible surface of Venus does not clearly preserve the first 4 billion years of its story. The oldest chapters are gone, buried, melted, covered, erased. That is one of the most haunting things about Venus. If ancient Venus had oceans, continents, shorelines, rivers, or habitable landscapes, much of that evidence may no longer be visible. The planet may have destroyed its own memory. On Mars, we can still see ancient river valleys. On the Moon, we can still see impact basins from the early solar system. On Mercury, craters preserve deep time. But Venus hides its past under a younger volcanic face. It is as if someone burned the first pages of a book, then sealed the rest behind clouds. So what happened? How does an entire planet get resurfaced? One idea is the global volcanic catastrophe theory, a planet-wide resurfacing event. Not one volcano erupting, not one region covered in lava, but a massive geological episode where lava spread across huge portions of the planet, perhaps over a geologically short period, burying older terrain beneath fresh volcanic plains. Imagine Venus after its oceans were already weakening or gone. The atmosphere thick, the heat rising, the surface dry. Then from below, the planet begins opening. Cracks form across the crust. Volcanic provinces awaken. Lava rises through fractures. Huge flows spread over the ground. Lowlands fill. Basins disappear. Ancient landscapes vanish under dark molten sheets. Highlands are surrounded. Valleys are buried. Whatever older features existed before are covered by a new volcanic skin. This is not the image of one mountain exploding like a familiar volcano on Earth. This is something larger, slower, wider, a planet resurfacing itself, a world pouring out lava until its own past is hidden. If there were ancient ocean basins, lava may have filled or covered them. If there were continent-like highlands, their edges may have been reshaped. If there were river valleys, sediment layers, or chemical signs of old water, many could have been destroyed, altered, or buried beneath volcanic deposits. Venus became a world where geology acted like fire over memory. And the cause may be connected to something Earth has that Venus does not appear to have in the same way. Plate tectonics. On Earth, the crust is broken into moving plates. These plates carry heat, recycle rock, bury carbon, build mountains, open oceans, and feed volcanoes. Plate tectonics is not gentle, but it helps Earth release internal heat over time. Venus does not show the same global plate tectonic system. Its crust may behave more like a stagnant lid, a thick outer shell that does not break into moving plates the way Earth's does. If heat builds beneath that lid for long enough, the planet may release it in rare, catastrophic pulses instead of steady recycling. Earth breathes geologically. Venus may have held its breath until it could not, and when that heat escaped, it may have done so violently. This would explain why the surface seems so young and so widely volcanic. Instead of continuous resurfacing through plate motion, Venus may have experienced huge resurfacing episodes that covered much of the planet at once. A global volcanic reset, a planet turning itself inside out. But lava was not the only problem. Volcanoes do not only release rock, they release gases. And on Venus, those gases became part of the planet's death. Carbon dioxide is one of the most important volcanic gases. On Earth, volcanoes release carbon dioxide too, but Earth has oceans, weathering, sediments, and plate tectonics that help regulate carbon over long timescales. Venus lost the systems that could balance it. So when volcanoes released more carbon dioxide into an already thickening atmosphere, the gas had nowhere effective to go. It stayed, it accumulated, it strengthened the greenhouse effect. The atmosphere became heavier, the heat became more trapped, the surface became more impossible. This is where Venus's destruction becomes a chain with many links. The runaway greenhouse dried the planet. The loss of water weakened carbon removal. Volcanism added more carbon dioxide. The carbon dioxide trapped more heat. The heat made the surface more hostile. The hostile surface prevented any return to an ocean-based climate system. The planet moved deeper into its new hell. Carbon dioxide did not arrive as one final blow. It arrived as reinforcement. The atmosphere had already become dangerous. Volcanism made it worse. This is one reason Venus's pressure today is so extreme. At the surface, the pressure is about 92 times Earth's. That is similar to the pressure nearly 900 meters below the ocean on Earth. But on Venus, this crushing weight is not water, it is air. A dense carbon dioxide atmosphere pressing down everywhere. Imagine standing beneath a sky so heavy It behaves almost like an ocean above you. No open human body could survive it. No simple machine could endure it for long without special design. Every surface lander must fight pressure and heat at the same time. The Venera probes that reached the surface were engineering miracles, yet they survived only briefly. Venus does not slowly inconvenience machines. It attacks them from every direction. Pressure crushes, heat penetrates, chemistry corrodes. The atmosphere surrounds everything like a hostile fluid, and volcanoes helped build that world. But carbon dioxide was not the only volcanic gas that mattered. Sulfur dioxide also played a major role. Volcanoes release sulfur gases, and Venus's atmosphere contains sulfur chemistry that helps create its famous clouds. High above the surface, sulfur dioxide can combine with remaining water vapor and other chemical processes to produce sulfuric acid. That acid forms cloud layers around the entire planet. These are the clouds that make Venus shine so beautifully in our sky. From Earth, Venus is bright because its cloud tops reflect sunlight. It looks clean, white, and brilliant. But that brightness hides poison. The clouds are made of sulfuric acid droplets. They wrap the planet in a toxic veil. They reflect sunlight back into space, but they also help define the nightmare world below. The atmosphere of Venus is not only hot and dense, it is chemically hostile. And in a strange way, Venus has acid rain, but not like rain on Earth. Sulfuric acid droplets can fall from the clouds, descending through the atmosphere. But as they fall lower, the heat becomes too extreme. The droplets evaporate before reaching the ground. So the surface of Venus is not wet with acid rain. The acid falls, then vanishes back into vapor before it can touch the rocks below. It is a broken rain cycle, a rain that never completes, a planet with clouds that cannot bring relief. On Earth, clouds can mean shade, rain, rivers, fresh water, life. On Venus, clouds mean sulfuric acid above a furnace. This is what makes Venus so visually deceptive. The outside is beautiful. The inside is dead. And the volcanic history of Venus may be the reason those clouds became so dominant. The planet's interior supplied sulfur. The atmosphere transformed it. The heat trapped it inside a circulation of toxic chemistry. Carbon dioxide, nitrogen, sulfur dioxide, sulfuric acid, trace gases, a thick, crushing atmospheric mixture unlike anything humans could breathe, a toxic soup covering an entire world. And beneath it, volcanoes everywhere. Some may still be active today. That possibility is important. Venus may not be a completely dead volcanic world. Evidence from surface changes, atmospheric chemistry, and spacecraft observations suggests that volcanic activity may still be happening. If true, Venus is not only a planet that suffered volcanic catastrophe long ago. It is a planet that may still be breathing fire, slowly, hidden beneath clouds, adding gases, changing its surface, continuing the same geological personality that helped transform it. This makes Venus different from Mars. Mars had volcanoes, including Olympus Mons, the largest volcano in the solar system. But Mars's major volcanic activity declined as the planet cooled. Today, Mars is mostly frozen and thin-aired. Venus stayed hot. Its atmosphere stayed dense. Its interior may have remained active. And because its surface is hidden from direct view, we are still trying to understand how alive its geology really is. The most terrifying possibility is that Venus did not only lose habitability through the atmosphere, it may have lost the evidence of habitability through volcanism. If there were ancient shorelines, sediments, hydrated minerals, or early crust shaped by water, a global resurfacing event could have buried them beneath kilometers or layers of lava plains. The planet may have once held the clues to its own better past, then destroyed them. That makes Venus a scientific tragedy. We are not only studying a dead world, we are studying a world that may have erased the crime scene. The volcanic catastrophe would have accelerated every other death mechanism. More lava meant more gases. More gases meant more greenhouse warming. More heat meant a drier surface. A drier surface meant less carbon removal. Less carbon removal meant thicker atmosphere. Thicker atmosphere meant higher pressure and more trapped heat. Sulfur gases meant acid clouds. Acid clouds meant a planet wrapped in corrosive chemistry. At every stage, the system fed itself. This is why Venus's death feels so complete. On some planets, one part of the system fails while others remain. Mars lost atmosphere but preserved ancient riverbeds. Mercury stayed airless but kept its cratered history. Earth suffered catastrophes but remained habitable. Venus lost the atmosphere-ocean balance and then buried the surface record, then built an atmosphere so extreme that even learning the truth became difficult. It destroyed itself from the outside in and from the inside out. From above, sunlight and water vapor pushed the climate toward runaway heat. From below, volcanism released gases and resurfaced the ground. The sky became a trap. The surface became a furnace. The interior became an engine of burial. Together, they created the Venus we see today. A planet not merely hostile, but transformed. Think of ancient Venus again. If it had oceans, the lowlands may have held water. The highlands may have stood above them. Clouds may have moved across a warm sky. The planet may have had coastlines, weather, and a climate that still belonged to the category of habitable worlds. Then the greenhouse strengthened. Water moved upward. Oceans shrank. Heat rose. The surface dried. Then the volcanoes came. Lava spread where water once stood. Basins filled with molten rock. Ancient landscapes disappeared. Carbon dioxide flooded the air. Sulfur built acid clouds. The pressure climbed. The last memory of oceans was sealed beneath a volcanic world. The sister planet became unrecognizable. This is why Venus is so hard to emotionally understand. It is not like looking at a planet that never had a chance. It is like looking at a house after a fire, knowing people may have once lived there, but the rooms are gone, the walls are blackened, and the records inside have turned to ash. Venus's volcanic plains are the ash of a planetary past. They are beautiful in radar images, complex, vast, mysterious, but they may also be a covering, a lid placed over the world that came before, and the scale is what makes it extraordinary. Earth has volcanoes, Mars has volcanoes, Io has constant volcanic activity, but Venus has a global volcanic character that feels uniquely tied to its climate death. It is not simply that Venus has many volcanoes, it is that volcanism may have helped lock the planet into its current state. Its geology did not rescue it. Its geology betrayed it. On Earth, volcanoes can be destructive, but they are part of a larger cycle. Carbon dioxide released by volcanoes can be removed again by weathering and oceans. Rock is recycled. The climate shifts, but the system has pathways back toward balance. On Venus, the pathways narrowed, then closed. Once the oceans were gone, the planet had no easy way to pull carbon dioxide out of the air. Once the crust resurfaced, older evidence was buried. Once sulfuric acid clouds formed, the atmosphere became even more alien. Once pressure reached crushing levels, the surface became a world where even robotic survival was temporary. The entire planet became a closed trap of heat and chemistry. And perhaps the most unsettling part is that Venus did not need to be hit by something from outside to become this. It did not require an invading force, no cosmic monster, no impossible event. The ingredients were ordinary planetary ingredients: sunlight, water, rock, carbon dioxide, volcanoes, atmosphere, time. The same kinds of things that exist on rocky planets everywhere. This means Venus is not just an exception. It may be a warning about how rocky planets can fail. Across the galaxy, there may be countless Venus-like worlds, planets that formed near the inner edge of habitability, held water for a while, then crossed a thermal threshold, lost their oceans, released their gases, and became bright, cloud-covered furnaces. From far away, some might even look promising at first, Earth-sized, cloudy, rocky, reflective, but beneath the clouds, dead. Venus teaches us not to trust appearances. A bright planet can be a grave. A cloud-covered world can be a furnace. A sister can become a warning. And when geology joins climate collapse, the transformation can become almost total. The volcanic catastrophe did not simply add drama to Venus's story. It helped complete the planet's death. It buried the past, thickened the air, fed the greenhouse, built the acid clouds, raised the pressure, and left behind the surface we are trying to decode today. A world with more volcanoes than any planet should need. A world where ancient history is hidden under lava. A world where the interior and atmosphere work together to erase habitability. So when we ask what killed Venus, we cannot blame only the sky. We have to look down, into the crust, into the mantle, into the volcanic heart of the planet. Because Venus did not simply burn under the sun, it erupted into its own tomb. There is one more reason Venus could not recover. Even after the oceans began to vanish, even after the atmosphere became thick with greenhouse gases, even after volcanoes covered the planet in lava and filled the sky with more carbon dioxide and sulfur, Venus still had one final weakness. It had no powerful magnetic shield. On Earth, we live beneath an invisible defense system. We do not feel it. We do not see it. Most of the time, we barely think about it. But above us, surrounding the planet, Earth's magnetic field reaches into space like a protective bubble. It is generated deep inside the planet, where motion in the liquid outer core creates electric currents, and those currents produce magnetism. This magnetic field does not make Earth invincible, but it matters. It helps deflect charged particles from the sun. It shapes the way solar wind interacts with our planet. It protects the upper atmosphere from being directly stripped away by streams of energetic particles. It guides dangerous particles toward the poles, where they create auroras instead of simply attacking the atmosphere everywhere at once. Those beautiful northern and southern lights are not just decoration. They are evidence of a planet defending itself. Earth has air because many things work together: gravity, temperature, chemistry, oceans, life, geology, and above it all, a magnetic field that helps reduce the damage from the sun. Without that shield, Earth would not instantly become Venus or Mars. But over long spans of time, the upper atmosphere would be more exposed. Solar wind would interact more directly, With the gases around the planet, atmospheric loss could become more severe, especially during strong solar storms and in the early solar system, when the young sun was more violent. A magnetic field is not the only thing that keeps a planet alive, but it is one of the things that helps life keep its home. Mars is the warning we usually think of first. Long ago, Mars had a global magnetic field. Then its small interior cooled, the dynamo weakened, and the magnetic field faded. Without that protection, Mars's atmosphere became more exposed to the solar wind. Over billions of years, much of it was stripped away or lost to space. The planet cooled, surface water disappeared, rivers died, lakes vanished. Mars became the dry, cold desert we see today. Venus is different. Venus did not become cold and thin-aired like Mars. It became hot and crushing, but it still shared one fatal problem. It had no strong global magnetic field. Either Venus never developed one like Earth's, or it lost it early in its history. And that absence may have helped seal the planet's fate permanently. This is one of the great mysteries of Venus. Why does Earth have a strong magnetic field, while Venus, so similar in size and mass, does not? The answer is still not fully known. A magnetic field requires a working planetary dynamo. Deep inside a rocky planet, electrically conducting material must move in an organized way, usually inside a molten metallic core. The motion of that liquid metal, combined with rotation and internal heat flow, can generate a magnetic field. Earth has the right conditions. Its outer core is liquid. Its interior is still hot. Heat escapes from the core into the mantle. The planet rotates once every 24 hours. The system keeps the dynamo alive. Venus, for some reason, does not have the same result. One possibility is that Venus's interior evolved differently. Maybe the core and mantle do not exchange heat in the right way. Maybe the planet lacks the kind of plate tectonics that helps Earth release internal heat and maintain long-term circulation. Maybe the core is not cooling in the right pattern to drive a strong dynamo. A planet can be hot and still fail to generate magnetism if the internal motion is not organized correctly. Another possibility is Venus's rotation. Venus rotates almost impossibly slowly. One Venus day is longer than one Venus year. It takes about 243 Earth days for Venus to rotate once, and it rotates in the opposite direction compared with most planets. The sun would rise in the west and set in the east if anyone could stand there long enough to watch it through the clouds. This slow rotation may matter. Rotation helps organize motion inside a planet's core. It helps shape the flow patterns needed for a global magnetic field. Earth spins quickly enough for its dynamo to stay strong. Venus rotates so slowly that its interior may not be able to maintain the same kind of magnetic engine. But even this answer is not simple. Some slow rotating bodies can still have magnetic behavior under the right conditions, and some fast rotating objects may not generate strong fields if their interiors are wrong. So Venus's missing magnetic field is probably not caused by rotation alone. It may be a combination: slow rotation, different core cooling, no Earth-style plate tectonics, different internal layering, a different geological history, a planet that looks like Earth in size but worked differently inside. That difference changed everything. Because once Venus began losing its water, the lack of a magnetic shield made the loss harder to stop. The sun does not only shine, it blows. The solar wind is a constant stream of charged particles flowing outward from the sun. On Earth, the magnetic field pushes much of this stream around the planet. On Venus, there is no strong internal magnetic bubble standing in the way. The solar wind arrives almost directly at the upper atmosphere. Venus does have something called an induced magnetosphere. This forms when the solar wind interacts with the planet's upper atmosphere and creates magnetic effects around it. It is not nothing. It does provide some structure and some resistance, but it is a poor substitute for a real global magnetic field. It is more like a temporary shield formed by the attack itself, not a deep planetary defense, not a strong internal bubble, not Earth's invisible armor. So when solar particles reach Venus, they interact directly with the upper atmosphere. They can energize atoms and molecules. They can help lift particles away. They can contribute to atmospheric escape. During stronger solar events, the damage becomes more intense. Every solar storm matters. Every coronal mass ejection matters. Every burst of charged particles from the sun hits a world that has no true magnetic protection. Now connect this with the water story. When Venus's oceans began evaporating, water vapor rose higher into the atmosphere. In the upper atmosphere, ultraviolet light from the sun broke water molecules apart. Hydrogen and oxygen separated. Hydrogen, being light, could escape into space much more easily. The solar wind helped carry it away. Atom by atom, across immense time, Venus lost the hydrogen that once belonged to water. This is one of the strongest clues that Venus had a wetter past. The planet has an unusual ratio of deuterium to hydrogen in its atmosphere. Deuterium is a heavier form of hydrogen, and because ordinary hydrogen escapes more easily, a planet that loses a great deal of water can become enriched in deuterium relative to hydrogen. Venus's atmosphere still carries that chemical ghost, a fingerprint of missing oceans, a sign that water was broken apart and that much of its hydrogen was lost to space. The oxygen did not remain as breathable air. It reacted with rocks, minerals, and surface materials. The hydrogen escaped. The oxygen was locked away. The water was gone. The missing magnetic shield did not create the runaway greenhouse by itself. It did not fill the atmosphere with carbon dioxide. It did not erupt volcanoes. It did not boil oceans alone. But it made the planet vulnerable at exactly the wrong time. Venus was closer to the sun. Its atmosphere was warming. Its oceans were evaporating. Its upper atmosphere was becoming loaded with water vapor. Ultraviolet light was breaking that vapor apart, and there was no strong magnetic field to help protect the escaping gases from the solar wind. The planet's defense system was missing during the most important crisis of its history. That is what makes Venus feel almost tragic. It did not fail in only one way. It failed in several ways at once. A little closer to the sun than Earth, a slower rotation, a missing magnetic field, a runaway greenhouse, a volcanic atmosphere, a loss of water, a lack of recovery systems. Every weakness made the next one worse. The greenhouse effect pushed water upward. The sun split that water apart. The weak magnetic protection allowed atmospheric escape to continue. Volcanoes added more greenhouse gases. The dry surface lost the ability to regulate carbon. The thick atmosphere trapped heat. The heat drove the system further from oceans, and each step made the planet less able to come back. This is what scientists mean when they talk about planetary feedbacks. A planet is not a simple object. It is a connected system. Atmosphere affects temperature. Temperature affects water. Water affects chemistry. Chemistry affects rocks. Rocks affect atmosphere. Volcanoes affect gases. Magnetic fields affect atmospheric escape. The sun affects everything. On Earth, many of these systems work together in a way that keeps the planet habitable. Not perfectly, not forever, but long enough for oceans, life, and civilization to exist. On Venus, those systems turned against each other. The atmosphere became a heat trap. The geology became a gas engine. The sun became a stripping force. The missing magnetic field became an open door. Venus had no defense against the combined assault. And once the water was gone, the story changed forever. A planet can survive many things if it keeps its water. Water gives a world options. It can rain. It can weather rocks. It can carry carbon into minerals. It can moderate heat. It can support chemistry. It can reshape landscapes. But a dry planet with a thick carbon dioxide atmosphere has far fewer paths back. Venus could no longer rein its way into recovery. It could no longer use oceans to absorb heat. It could no longer use water-rock cycles to bury carbon efficiently. Its sky became heavy. Its surface became dry. Its memory of oceans became chemical residue. The missing magnetic field helped make that loss permanent. This is where Venus becomes different from a temporary climate disaster. A temporary disaster can fade. A planet can warm and cool. Ice ages come and go. Volcanoes erupt and quiet down. Asteroids strike, and life can recover if the planet's basic systems remain intact. But Venus lost one of the ingredients that could allow recovery. It lost water into space. You cannot easily rebuild oceans after hydrogen has escaped into the void. That is what made the death sentence complete. The planet did not just become hot, it became unable to become wet again. And without water, every other problem hardened into place. The pressure grew, the atmosphere thickened, the heat remained, the clouds became sulfuric acid, the surface became volcanic and barren. The planet's interior, atmosphere, and star all became part of the same locked system, a stable hell. The phrase sounds strange, but that is what Venus is today. Not a planet in the middle of dying, a planet that has already settled into death. Its atmosphere is massive. Its surface is hot everywhere. Its pressure is crushing. Its water is almost entirely gone. Its magnetic shield is absent. Its clouds reflect sunlight beautifully while hiding the furnace below. It is not trying to return to Earth-like conditions. There is no easy path back. That is the cruelty of planetary thresholds. Before the threshold, change can be resisted. After the threshold, the new state becomes self-sustaining. Venus crossed too many thresholds. Climate, water, geology, magnetism, atmospheric escape. All of them together created one of the most complete transformations in the solar system. And this is why Venus is so important for Earth. Not because Earth is about to become Venus. Earth is not Venus. Our distance from the sun is different. Our oceans are different. Our atmosphere is different. Our magnetic field is strong. Our geology is different. Our biosphere is active. The future of Earth is not a simple copy of Venus. But Venus shows us that habitability is not guaranteed forever. It shows that being Earth-sized is not enough. Being rocky is not enough. Having clouds is not enough. Even having water once may not be enough. A planet must keep its balance. It must keep the systems that protect water atmosphere, and climate from sliding too far in one direction. Earth's magnetic field is part of that balance. Not the whole story, but an important part. It helps us keep the upper atmosphere from being stripped too aggressively. It helps reduce the direct impact of solar wind. It helps preserve the environment in which oceans and life can continue. Venus reminds us what a planet looks like when many defenses fail. Mars reminds us what can happen when a small world loses its magnetic protection and atmosphere. Venus reminds us that a larger world can lose protection too, but follow a different path. Not into freezing emptiness, but into crushing heat. Two planets lost their balance. One became cold, one became hell. Earth remains between them. That is why the inner solar system feels like a lesson written in three worlds. Mars says a planet can dry and freeze. Venus says a planet can overheat and suffocate. Earth says balance is possible, but also fragile. The factor that sealed Venus's fate was not simply the lack of a magnetic field. It was the lack of a magnetic field at the same time as everything else was going wrong. That is the perfect storm. The runaway greenhouse made the oceans vulnerable. Volcanism made the atmosphere heavier. The missing magnetic field made water loss harder to stop. The solar wind carried away what ultraviolet light had broken apart. The dry surface removed the planet's ability to regulate carbon. The pressure and heat locked the system into place. Three death mechanisms working together: atmosphere, geology, space weather, each one feeding the others, each one closing a door. And by the time Venus might have needed a rescue, there was no ocean left to save, no magnetic shield to rebuild, no cooling cycle strong enough to return, no rain to cleanse the sky, no carbon cycle like Earth's to pull the atmosphere back from the edge. It was already too late. That is the true horror of Venus. Not just that it died, but that its death became irreversible. A planet can drift toward disaster slowly enough that nothing looks urgent at first. A warmer ocean, a wetter atmosphere, a little more gas, a little more volcanic activity, a little more atmospheric escape, a little less protection. Then one day, geologically speaking, the systems that once held the planet together begin to amplify the damage. And after that, the planet does not fall apart. It becomes something else. Venus became something else. The sister of Earth became a world with no real shield, no oceans, no breathable air, no gentle surface, and no memory left except chemical clues in the atmosphere and strange terrain beneath the clouds. A bright planet in the evening sky, carrying the story of a lost ocean, a failed shield, and a world that had no defense when the sun came for its water. Venus is not only a planet, it is a warning placed almost next door. It shines in our sky brighter than any star, often appearing after sunset or before sunrise, calm and white, as if it has nothing terrible to hide. For thousands of years, humans looked at it with wonder. Ancient civilizations named it, tracked it, worshipped it, built calendars around it. To the naked eye, Venus is beautiful. But beauty from a distance can be misleading, because beneath that bright cloud cover is the most important lesson in the solar system. Venus teaches us that a world can look like Earth in almost every basic way and still become something completely different. Earth and Venus were born from the same young solar system. They formed from the same disk of dust and rock around the same newborn sun. They grew in the same inner region. They became rocky planets. They reached similar sizes. Their masses are close. Their densities are close. In another life, Venus should have been our twin. Not identical, but close enough that scientists still compare them like siblings. And yet today, Earth has oceans, continents, breathable air, forests, rivers, animals, clouds, rain, and life. Venus has crushing pressure, acid clouds, a carbon dioxide atmosphere, volcanic plains, and a surface hot enough to melt metal. One became paradise, one became hell, and the distance between them, in cosmic terms, is almost nothing. Venus orbits closer to the Sun than Earth, but the gap between their orbits is only about 40 million kilometers at closest approach. That sounds enormous to us, but compared with the scale of the solar system, compared with the distances between stars, compared with the vast emptiness of space, it is tiny. Two planets, almost the same size, born at almost the same time, separated by only a small step outward from the Sun. And that small step helped change everything. Earth sits just far enough away, not too close, not too far, close enough for sunlight to warm the oceans, far enough that water can remain liquid on the surface. That is one of the luckiest accidents in our history. Earth's distance from the Sun is not the only reason life exists here, but it is the first condition. If Earth were a little closer, our climate history may have been more unstable. If it were much farther away, the planet might have frozen more deeply. The position of Earth allowed the rest of the systems to work. Venus was closer. It received more sunlight. At first, maybe that was not fatal. Clouds may have reflected sunlight away. Ancient oceans may have survived. A wet Venus may have remained stable for a very long time. But the margin was smaller. The line was closer. And over billions of years, small differences become planetary destinies. That is the first lesson Venus gives us. Habitability is not a guarantee. It is a balance. A world does not become Earth-like simply because it is rocky, or because it has the right size, or because it has water at one point in its history. It must keep those conditions stable across deep time. Earth did, Venus did not. And the reasons are written into the systems that still protect us now. One of those systems is Earth's magnetic field. Every day, the Sun sends charged particles outward through space. The solar wind touches every planet, but Earth is not exposed in the same way Venus is. Around our planet, the magnetic field acts like an invisible shield, guiding much of that particle flow around us and helping protect the upper atmosphere. We rarely think about it. We live beneath it without noticing, but everything we have ever known has existed under that protection. Every city, every ocean voyage, every forest, every civilization, every human life. Earth's magnetic field is one of the quiet reasons our sky still belongs to us. Venus does not have a strong global magnetic field like Earth. It has only an induced magnetic environment formed by the solar wind interacting with its upper atmosphere. That is not the same as a deep internal shield. So when Venus began losing water, when hydrogen was being broken from water vapor and escaping into space, the lack of a strong magnetic defense made that loss easier to continue. Earth kept more of its protection. Venus did not. But magnetism is only one part of the story. Another system may be even more important: Earth's carbon cycle. This is the quiet machine that has helped regulate our climate across millions and billions of years. Carbon dioxide enters Earth's atmosphere through volcanoes, fires, biological processes, and other sources, but it does not simply accumulate forever. Rainwater absorbs carbon dioxide. Oceans absorb carbon dioxide. Weathering breaks down rocks. Carbon becomes locked into minerals, sediments, shells, and eventually deeper layers of the planet. Over long timescales, plate tectonics helps recycle that carbon. Some carbon is buried, some is carried into the mantle, some returns through volcanoes. It is not a perfect system. It does not keep Earth's climate exactly the same. Earth has had ice ages, warm periods, mass extinctions, and dramatic climate shifts. But the carbon cycle has helped keep the planet within the broad limits where oceans can survive. It is one of Earth's great planetary stabilizers. Venus appears to lack Earth-style active plate tectonics. Its crust does not seem to recycle itself in the same steady way. Instead, Venus may have stored internal heat beneath a stagnant outer shell, releasing it through enormous volcanic episodes. Without oceans and active rock weathering cycles like Earth's, carbon dioxide had fewer paths out of the atmosphere, so it accumulated. Volcanoes released gases. The atmosphere thickened. The greenhouse effect intensified. The planet lost the ability to regulate itself. That is the difference. On Earth, carbon moves through a cycle. On Venus, carbon became a prison. This is why Venus matters so much now, because Earth is also changing its carbon balance. The comparison must be made carefully. Earth is not about to become Venus. Our oceans are not boiling away. Our atmosphere is not 92 times thicker than it should be. Our sky is not becoming sulfuric acid. The timescales, conditions, and planetary systems are different. But Venus shows the endpoint of a world where greenhouse gases dominate completely. It shows what happens when heat becomes trapped beyond recovery. It shows that carbon dioxide is not just a number in the air, it is a planetary force. On Earth, rising carbon dioxide is already changing climate, warming oceans, shifting weather patterns, melting ice, and increasing risks for ecosystems and human societies. This is not Venus-level danger, but it is real planetary stress. Venus does not say Earth will become Venus tomorrow. It says, respect the systems that keep planets stable, because the same kind of physics exists here. Greenhouse gases trap heat here too. Feedback loops exist here too. Oceans and clouds and ice and atmosphere respond to warming here too. The difference is that Earth still has working stabilizers, still has oceans, still has rain, still has plate tectonics, still has a magnetic field, still has a living biosphere, still has time. Venus shows what happens when a planet loses the ability to pull back. That is why scientists call it Earth's evil twin. Not because it is supernatural, not because it is cursed, but because it shows a version of Earth-like beginnings that went wrong. It is familiar enough to be frightening. If Venus were completely different from Earth, it would be less disturbing. If it were a giant gas planet, or a frozen moon, or a tiny asteroid, we could separate ourselves from it emotionally. But Venus is close. Venus is rocky. Venus is similar in size. Venus may once have had oceans. That is what makes it terrifying. It is not alien enough. It is almost us. And this lesson now reaches beyond the solar system. Astronomers have discovered thousands of planets around other stars. Many are rocky worlds. Some are close in size to Earth. Some orbit near the inner edge of their star's habitable zones. Some may receive too much sunlight to keep oceans stable for long. This region is sometimes called the Venus zone, the area around a star where a rocky planet might resemble Venus more than Earth. It may be Earth-sized. It may have clouds. It may even have had water once. But if it is too close to its star, it may face the same fate: runaway heating, water loss, thick atmosphere, and permanent uninhabitability. This changes how we search for life. Finding an Earth-sized planet is not enough. Finding a planet near the habitable zone is not enough. We must ask deeper questions. Does it still have water? What is its atmosphere made of? Has it lost hydrogen to space? Does it have signs of a runaway greenhouse? Does it have clouds that hide a furnace below? Is it truly Earth-like? Or is it Venus-like? The universe may be full of dead Venuses, planets that almost made it, worlds that formed with the right ingredients, held water for a while, maybe even stayed habitable for long stretches of time, then drifted past the edge and never came back. From far away, some of them may look beautiful: bright clouds, rocky sides, sunlit atmospheres. But beauty does not prove life. Venus teaches caution. It tells us that habitability is not just a location around a star. It is a history. A planet must survive its own star, its own geology, its own atmosphere, and its own feedback loops. A living world is not a simple object. It is a long-term negotiation between forces. Earth has negotiated well, so far, and that is what we must protect. The magnetic field, never take it for granted. The atmosphere, never treat it like an infinite dumping ground. The oceans, never forget that they are part of Earth's climate engine. The carbon cycle, understand that it is one of the most important systems on the planet. The distance from the sun, recognize it as one of the luckiest accidents in the history of life. We did not choose to be born on the right world. We inherited it. We inherited a blue planet that still has rain, clouds, rivers, ice, soil, forests, coral reefs, winds, seasons, and breathable air. Venus reminds us how rare that is, because next door there is another planet almost our size that lost all of it. No ocean remains, no blue sky, no soft rain, no cool night, no open future for life on the surface, just clouds above clouds, pressure beneath pressure, and heat that never ends. This does not mean Earth is fragile in the sense that it can break from one mistake. Earth is strong. It has survived asteroid impacts, ice ages, volcanic disasters, oxygen revolutions, mass extinctions, and continental rearrangements. Life is resilient. The planet is dynamic. But Venus tells us that resilience has limits. The line between stability and collapse may be wider for Earth than it was for Venus, but it is still a line. An intelligent life should not test that line carelessly. That may be the deepest lesson. Venus is not only a scientific case study, it is a moral mirror. It asks whether a civilization can recognize the value of a stable planet before it damages the systems that make stability possible. It asks whether we can understand deep time while living in short human lives. It asks whether we can look at a bright dead world in our evening sky and understand that the difference between worlds can be measured in small margins, repeated across billions of years. Venus did not become hell because it was ugly. It became hell because physics does not care about beauty. A planet can shine brilliantly and still be dead. A world can look peaceful through a telescope and still have a surface no machine can survive for long. A sky can be bright and still be poison. That is why the final image of Venus is so powerful. From Earth, it is the evening star, a point of light over oceans, cities, deserts, mountains, and sleeping homes. People see it and make wishes. They photograph it beside the moon. They watch it from balconies, beaches, rooftops, and quiet roads. It looks like a symbol of calm. But science has taught us what is beneath. The brightest planet in our sky is a warning label written in clouds. It says, "This is what happens when balance is lost." It says, "Earth's beauty is not automatic." It says, "Protect the systems that protect you." And still, Venus is not only frightening, it is also valuable. Because by studying Venus, we understand Earth better. We understand climate better. We understand exoplanets better. We understand the inner edge of habitability better. We understand that planetary survival is not about one factor, but many. Distance, atmosphere, water, magnetism, geology, chemistry, time. Venus failed because too many of those systems turned in the wrong direction. Earth survives because enough of them still work together. That is the contrast that should stay with us. Not fear alone, gratitude, because Earth is not normal in the way our daily lives make it feel. A blue sky is not ordinary. Liquid oceans are not guaranteed. A breathable atmosphere is not automatic. A stable climate is not a permanent gift. A magnetic shield is not something every world receives. A working carbon cycle is not a detail. It is part of the reason everything we love exists. Every forest, every river, every animal, every city, every human story has happened inside a narrow band of planetary balance. Venus reminds us that this balance can be lost, and once lost, it may not return. Tonight, as you drift to sleep, if the sky is clear, look toward the west after sunset or toward the east before dawn. Find that brilliant white light that does not twinkle like a star. That is Venus, our neighbor, our sister, the brightest natural object in the night sky after the moon. Beautiful from here, dead up close, a world of crushing pressure, acid clouds, volcanic plains, and temperatures hot enough to melt metal. It may not have had to be this way. Venus may once have had oceans, maybe highlands like continents, maybe clouds that cooled it, maybe rain, maybe time, and then it tipped, slowly at first, then completely, past the point where water could stay, past the point where the atmosphere could cool, past the point where the planet could return. And now it remains there, wrapped in bright clouds, shining over Earth like a ghost of what might have been. Tonight, Earth is still blue. Our oceans are full. Our skies open. Our magnetic field holds. Rain still falls. Clouds still move. Life still breathes. But Venus reminds us that nothing in the universe promises this forever. The line between paradise and hell is not as wide as we wish. Sometimes it is measured in distance from a star. Sometimes in carbon buried or released. Sometimes in water kept or lost. Sometimes in a magnetic field we cannot see. And sometimes in whether a world understands its warning signs before the final threshold is crossed. So sleep now under Earth's gentle sky. Breathe the air Venus lost forever. Dream beneath the protection of a planet still alive. And remember the bright white world near the horizon. Our sister, our warning. The planet that teaches us, more clearly than any other, that a home in the universe is not something to take for granted. Good night.